there are a few different stations. Primary work I'm doing, this experimental space-time distortion work. That's over here in this area I'm building up. And I'll describe what's going on there in a second. Also doing some work with robotics, and we have this kit that we've created that's a 3D printable robot that is really to teach students STEM skills. You can grab chairs if you want. Teach students STEM skills, all around by having a really interactive, hands-on type of thing. Here's some 3D printers. Got some electromagnetic stuff I can do over here. Another kind of workstation to build. I'm in the midst of not only moving things around, but kind of reassembling the test. So if I go over here, one of the things I'm doing with the interferometers, you need a really stable platform, and I had a smaller optical kind of table right there. But in order to take this vacuum chamber and be able to put that in the midst of the interferometer setup, I needed to expand the distance, and so I need a bigger table. And
big optical bench.
Yeah. There's a couple that are here, so I'm either going to have to move my setup to where it is, move it in here, or purchase a new one altogether.
They're heavy.
None of those are actually really great options.
So with this one, you're doing, it's a spark gap, and then you're doing interferometry through the explosion area, right?
Yeah, let me show you.
I'm sorry, Tony.
Got it to a point where, so right now this spark is inside the chamber, and I will actually turn it on. Yeah. One of the things I do is I can modulate to a point. I can modulate the speed at which the spark is formed, because one of the things I really put forward in the paper was that this change in energy density with respect to time is important, and so I want to be able to basically turn it off and on, but also, as you know, in the vacuum chambers, I'm able to get the air out. The formation of the plasma is going to change its characteristics. So I'm going to actually turn this on. So I have this signal generator gets this signal gets amplified through this amplifier to a voltage high enough to initiate the spark, and I wanted to do that so that I can change its speed and either go faster or slower within reason. But I also have I do have a hypothesis I'm working on that is going to say that the frequency of the introduction of the energy also has some effect. And just quickly, the basis is that when you look at data from the from LIGO and from black hole mergers, you see a ringing that occurs in space-time after they form, and that essentially says that there is some sort of elasticity to space-time. Mm-hmm. Now, if we are doing it on a smaller scale, because you can measure the mass of the two black holes that merge and get the ringing that occurs due to that, and then see if there is an analog at much smaller masses, what frequency would that be the ideal frequency? So that's just something I'm working on. I'm going to try to publish something later on that. Now, and I apologize, it's kind of warm in here, because it's cool everywhere else in the building but in here for some reason.
Oh no, you know what? I am so grateful for you having a sober
So I'm gonna. You could get a shot
You
of.
gotta close that valve.
Yeah, I'm going to.
You have a nice shot to hit this side.
Well, I don't think I can get the valve that way, but
Well, you could.
there we go. I can get the spark though.
Yeah. Okay, I can get this to almost minus 100 kilopascals down from a normal atmosphere. So it's nearly a perfect vacuum, but not quite. But as you can see now, the plasma is not forming. So but you do see that you get there's stimulated emission. So there is energy being transformed from
You got a argon glow there, right?
yeah. So I can close this valve. All right, so the vacuum is still holding. And so now what I would be doing next, if I get all of this on an optical table, I would, assemble this appropriately and get the interference fringes that I could then image and get data on and see if there is an effect with this now changing energy source
So
across.
where's the laser light go through? Does it go through in the?
Yeah, right through the middle, through the tip, from where the tips emerge. And
So you're seeing a change even when the sparks are not happening, like when
I
under vacuum?
haven't tested that yet.
So you tested it only on your ear?
Yeah.
So if the laser goes through when it's a vacuum like that, right, and you got this corona around the electrodes, right? If the laser is going through that corona,
Yeah.
it's going to have like some other thing, right? So is what you're trying to do like increase the field strength of that corona as much as possible?
Yeah.
And then as the laser light goes through the corona, it'll shift
Yeah.
somehow in a measurable way.
Yeah.
How do you identify whether or not that's like metric changes or whether or not that's just electrostatic changes from the corona?
Yeah, I mean that's really part of the whole question. Now, that same question could be asked when it's in the air, and some of the things we've done, like so we've used two different wavelengths of light. Also looked at it from different angles to try to overcome, take advantage of Snell's law. If it is index of refraction, then, but so the measurements that I had didn't show appreciable difference with any of those different changes, and that's what's led me to believe.
Are you doing the experiments with that argon glow in there?
I'm going to.
Or are you going down further to get rid of the
I'm
glow?
going to try to go down further. It's just making sure all.
You can also go down as low as you can, backfill it with CO2 or nitrogen and bring it back up, and you can get a white glow instead of the argon glow.
So you'd mentioned if folks wanted to replicate this, then
Are you running it on this table?
No, I'm going to move it when.
Well,
once I-
were you running it on this table?
I was running it on this table with that.
That's a
That's an optical.
isolation. Does it
Yeah.
have like air foot pads?
Yeah, well, yeah, it had not air foot pads, but it has it mitigates the vibration.
Oh, vibration.
Plus, we were able to. The other thing is that the movement that I saw varied as we moved it closer or further away from the spark. So if you move the spark, just say 20 millimeters away from the laser, you saw no movement, even though everything was still on the table. Any vibrations that were there were still there. So it was whatever activity within that particular.
So the physical vibrations were still present because it was on the table.
Yeah,
And you were
yeah.
just moving it into the optical beam path.
Yeah.
But a spark like that would change the refractive index of air.
Yes, and that's what I was getting at with the questions before, was looking at different wavelengths and looking at different incidence angles
okay.
to make sure that, because if it was index of refraction and different angles would show different performance, plus different wavelength of light would show a different performance.
We built a laser interferometer at my lab with a base made out of G10, which is like a plastic mixed with glass polymer, and it's about as stiff as aluminum. So it's a really nice material to work with. So if you want to do high voltage sparks or anything, you wouldn't interference from a metal table.
Oh, I see.
I might can get you a very large piece of that honeycomb aircraft stuff that's pretty stiff.
But it's metal.
It's metal.
Yeah,
This is, I like the simplicity of it because that makes it seems like this would be easier for people to replicate, right?
And that was what the point you were making. Yeah, I mean, and that's what I invite people to do because, I want to just make sure we're on the right track and doing the right things, and a scientific experiment that's reproducible is one of those things.
Yeah, and that's I love the simplicity of it. I mean, again, going back in here, basically it's a spark gap inside of a little vacuum chamber, and then you're just doing interferometry on it. And I do like the fact, so you're using different wavelengths, if I interpret this correctly, you're using different wavelengths so that you can basically isolate out the change in space-time distortion.
Yeah, and to kind of mitigate the issue of whether or not it is index of refraction versus some other mechanism, we did things to rule out other mechanisms. It is in the paper that, but I think I gave you the link for, and everybody should be able to pull it up. So, read that and see if those things we did to try to overcome makes sense.
Yeah, that's exciting. This is really exciting.
Link with us at some point?
Yeah.
Okay, I mean, and it's right there.
Now, Chance, I should also ask, I know I'm changing topics. You were doing bubble collapse research too, right? Were you doing that here?
I wouldn't call it bubble collapse. What I was doing was I started with the equations out of Alcubierre's work.
Okay.
Looking at the energy density equations, and said, okay, given that is the energy density, if we introduced a complex variable in those equations, the negative energy density goes away. And then from that point, we tried to concoct an experiment to do that using a material that has a complex dielectric constant in a chamber. Matter of fact, this little chamber I had over here was what we started trying to fill with this material.
Wow. Okay, let me zoom in there.
The problem was I wasn't able to get enough RF power to feed into this chamber. That's where we, if you recall, borrowed your amplifier. I was going to use it around, because this is built for around 2.4 gigahertz with the material in it. And we just weren't able to generate enough power to even think that we were going to see anything with that. So, I mean, it's still a possibility because mathematically it makes sense. It's just whether you can actually do this in practice. But here's where I went with that. The complex values actually introduce a rotational action with the RF fields that are inside. it's this, it creates, and so I started to go next with this using a circularly polarized, I don't know where the other one is, but this is one of them, circularly polarized antenna. And the fields would just spin around here at the speed of the frequency that you introduce. As long as this delay is enough, that's like a 90 degree phase shift, and you feed it, and now the fields will circulate. So I use this to try to introduce a circulation instead of using the complex dielectric constant. But that in itself, we still weren't able to generate enough power to see.
Why is the main antenna part square? Why don't you have it round?
That's easier to. It was easier to fix it at a frequency that I wanted using a square versus and it was easier to. Lock in. It could have been round.
You know, I'm so excited that you're doing this work. I mean, there is virtually no one doing active like warp drive research, right? You have a couple of folks doing a couple of projects, right? Like Mark's one of those, Jared's doing a couple of things, you know, Tony's starting to work on superconductor stuff. But this area, I mean, there used to be so many more people involved in it than there are today. So the work that you're doing is incredibly valuable.
Well, you know, you can write about and argue about the math, and it's very important to do that. But at some point, you have to try to see if things physically work.
Yeah.
You can make the math spit out answers that you want anytime.
Yeah. I mean, you know,
It's the experiments that really tell you which part of the math is correct.
reproducible
Magic.
Yeah, but, you know, you flip a sign and you know, everything changes. I mean, it's just like with the energy density equation, you know, to say, okay, the big thing, you can't do this because it requires negative energy density, so you can't do it. That's what's the word after Alcubierre's work.
Yeah.
But as people, you know, begin to just be stubborn about that instead of just...
The definition of energy density is something you have to define before you can really talk about it. Because the negative energy density, from my perspective, is just energy density that goes in the opposite direction of a gravitational force.
See, you're right, and here's I mean, as far as what I understand is what I'm meant to say. You're right, like I'm pronouncing it, but you know, but what was something to be noted with Alcubierre's work is that he says you have to have a expansion behind your ship and a compression in front. So the expansion kind of pushes you and you get pulled here, but things in nature and energy, mass, all that we know of all compresses space-time. We don't observe anything in nature that expands space-time, except what they believe on the outer edges of the.
It pulls it.
Yeah.
It pulls it in.
Yeah.
Doesn't push it out.
So my interpretation of that was that a negative energy density is required to expand space-time, and it kind of makes sense because of positive energy and positive mass compresses it. So, and that's why some net negative energy density is required in his formulation. And you know, I wasn't really looking at trying to reproduce his thing. I just wanted to say, could we distort space-time in a laboratory?
Yeah.
That was the question I wanted, and then we can figure out what else.
Question on the distortion, the metric change you want to look at here. Assuming you got a nice, quiet optical bench, any prediction on signal-to-noise ratio that you'll have here?
I hadn't set up a measurement for that, but you mean between the
Between the metric change you're trying to measure and all your noise inputs.
It's pretty.
And how long do you want to integrate the
30 dB
effects?
or more is expected because it's a pretty pronounced effect. I mean, with the data I have already.
Yeah, so you should be in tens, hundreds of a ratio.
Yes,
Okay.
yeah, because you know, we know the variations on what we're providing, and we see those same variations in the movement of the fringes.
Okay.
And so, you know, got good data on the fringe
Okay.
movement.
All right.
Are you doing this during regular semester, or you do it mostly? Because the building is amazing right now. It's probably very low vibration.
Right.
When
Yeah,
there are people
that's what I'm
walking
thinking.
by, I can
Yeah.
imagine.
Yeah.
Bounces all over the place.
Yeah.
I come in a lot on the weekends, and I'm in the evenings and stuff like that. Most of the
That would
time,
be much better time. Yeah, you should consider that in your research, because people walking past here can
Yeah.
add a lot of noise to this.
And it'll be run when that pump's off, right? The pump's not running
Yeah,
when you're trying to.
yeah. That's why it can hold it pretty well.
We had a gravity meter that we rented when we was doing the souped up gravity experiments to pick the traffic up driving down the street.
So, what are y'all's backgrounds? If you don't
Yeah,
mind, just
yeah.
kinda-
So I've been part of this aerospace corporation. Have you heard of Greg Mahalik? Greg Mahalik is a researcher at aerospace, and he pulled me in to consult on some of the experiments he was doing in this area. And they found, like Glen was mentioning, that even the traffic out on the main road, and they had a very isolated lab at aerospace. Even that had an impact, so they had to do it at night when everything was quiet. And they have problems with their signal to noise in that experiment. So that's why I was asking about. But you're using a laser interferometer, which is not what they were using. So they were doing more of a balance.
Oh, yeah.
Torsion balance.
Yeah,
scheme.
that's gonna.
And that's not as
very-
sensitive as what you're doing with the laser interferometer. And I like that you're using two different frequencies, so that should help.
Because I saw, movement variation in the fringe movement on the order of 70 to 100 nanometers
Okay.
of movement. Now, you have to take into account how far away you have everything on that. But once you do, you can calculate what you believe is the stress, and it's pretty good. It is beyond what you would calculate. That's
Sorry about that.
it didn't look like anything important.
That's your latest number, right?
There we go.
Yes, that's it.
It does say 2025. I'll read through it.
This is it right here. I brought it up. So I can.
If your laser is going through the plexiglass, right, and through open air and all that,
Yeah.
this is all electrostatic, then wouldn't that mean that you're going to have electrostatic fields that you're getting Kerr effects on your plexi, you're getting additional electrostatic like effects where you don't want them? So wouldn't it be better to have the whole thing set up in a Faraday shielded vacuum chamber?
Ultimately, yes. You're right. And I'm kind of taking
Baby steps.
Yeah, because this is the first I've done it try to do it in a vacuum chamber, because I want to, there's been more questions about, okay, you did do this, you didn't do that, so I want to kind of meet those questions. Why we escalate the energy input. Also doing you mentioned a torsion balance to, try to see if there's any kind of actual thrust that occurs. All of those things would be kind of just stepping further and further.
So if I can get an email or something from you. So my partner Charles Crawford and I, we went over to Kepler Aerospace a year and a half or two ago. We were using the exact same high voltage and everything there, and we were doing the Campbell thruster inside there, right?
Okay.
And once you get down to about 10 to the minus 2, right? That's when you're that's when you're seeing, coronas and stuff. But then you get down to 10 to the minus 3, and that corona starts blooming up real big. And you go down to strong 10 minus 3, and that corona is just filled up. We had this bubble chamber that was about a meter diameter, right? And that corona, eventually we just did arcs, right? We just said, well, let's just see what an arc looks like under this. And so we took the two parts of that and just, 1 inch gap.
Sure.
And that 1 inch gap, eventually you get super diffuse pink glow that just fills the whole chamber because the atmosphere is so diffuse in there. And then we tried playing around with putting different gases back in there.
But what's the mechanism in the vacuum that's creating that glow? I mean, there should be some chemical or something.
No, it's the that mean free path is getting so large by 10 to the minus 3, and so what Drew over in Florida has figured out with his TT Brown thrusters he works on is that electrostatics and vacuum, it gets worse and worse until you get past 10 to the minus 3, and then it starts improving. And for our TT Brown experiments, it wasn't until you get to strong 10 to the minus 5 until really 10 to the minus 6 before your TT Brown effects are even seeming to come to play, right?
Yeah, ion wind dominates in the -5 arena and below. And it's the strongest in the -2, -3 range. So if you used your roughing pump and pumped as much as you could, that's plexiglass too, you'd probably get to mid-2s. You're going to have a lot of ion wind in there.
So you're going to have maximal corona, if indeed that's what you'd like to test through, but you're not going to be able to get to minimal corona, right? minimal corona would be like 10 to the minus 9 or something, right? You're
It'd be
getting
easier to use sulfur hexafluoride and just do away with the whole vacuum chamber thing. Sulfur hexafluoride in atmosphere is better than the vacuum levels that you'd get with that vacuum pump. And because that's plexiglass, there's no way to pump it down enough.
Yeah.
That
Well, that's why you had that thing over there.
Oh, that'll pump down nicely.
If that's your-
But I can't figure out how to do interferometry.
I'll read your paper and try to understand what you're doing more, but it seems to me that your experiment would be more effective if you can get down low enough where you have almost no atoms within with the space you're trying to measure. Because any atoms, a certain density of atoms between there, that's going to affect your measurement altogether.
You have access to sulfur hexafluoride?
I'm pretty sure I can.
Mark might be able to.
That puts a lot of atoms in your space.
Mark might be able to get some for you.
He's talking about putting a gas in there and doing the experiment in the gas. That's a lot of big atoms that are floating around in that gas.
Yeah.
You want to get rid of as many atoms as you want to if you're looking for something for a
Because one of the first things I
electrostatic effect of
started
space-time.
doing was helium.
Yeah, you're right.
Which was using helium
Yeah.
in there, but it was to try to have more of a noble gas that wasn't gonna arc as quickly, but the effect actually almost like an increase.
I don't fully understand your experiment, but if you're looking at some effect on space-time, then to me you won't hardly no atoms in there at all. If you want to try to affect space-time, but then again, I don't know exactly.
Yeah, well, no, I mean that's what I want enough energy. I want to create enough energy density between the tips within it, basically with.
You basically want to have a pure electrostatic field there
Yeah.
with no elements moving around in that field. Then you have an energy density between those fields that you want to interact with that. So yeah, you really want to get rid. You want to go to as low a vacuum as you can. That's what I'm saying.
So do you think if you do higher energy pulses, right? Like right now, it looks like it's kind of a frequency-based, wave-based, like I don't know what you call, almost like a Tesla coil output, right? But like if you went to like a Mark's discharge through there, do you think that you might see more distortion?
In the end, is about increasing the energy density, and one of the curves I have here. Where is it? Oh, come on. Oh, here we go. Yeah. So this here is a measure of the displacement versus the energy density and that was even though we increased the input power, but the distance of between the sparks was longer, so you had a greater volume, so the energy density actually was lower, even though the power was higher. But the energy density drove the fringe effect, not the power, not the input power level.
Well, getting back, that's Mark from Falcon Base.
Yeah.
You know him.
Yeah.
I go by Tony Robertson, but if you look me up, it's mostly Glen A. Robertson online.
Okay.
I'm retired from NASA. I was the original founder of the NASA gravity team, superconductor gravity team. Then it was turned over to Ron Kozar in the second year of the project.
How is Ron, by the way?
I haven't seen him since he retired.
I worked
Yeah.
for him at one point.
Oh, did you?
Yeah, when he was at ITT though. If I write down an email address, would you send me a link to your paper?
Yes. Yeah, you could write it there, or we got phones, I'm sure we can.
Yeah. Well, and Glenn, again, thank you so much for walking us through this.
I mean, I appreciate you being interested enough to come by and talk about it. I just want to keep, pushing this. I mean, as you can see, these are some of my muses, I guess. And, I love Star Trek. That's inspired everything I've, been doing recently. And, I want to see some of these technologies come to life,
You need to put the girl from Discovery up there. Star Trek Discovery?
Oh, yeah. But he's my guy. That's my
Well, so
all-time favorite.
So with this experiment, do you have a next step? Actually, before I close this one out, do you have a next step for what you're going to do?
Well, I mean, the next step was to introduce a vacuum and remove some of the issues around plasma and that discharge and all that, to just try to get as much pure energy density and see if we have effects. Also, a torsion balance type of experiment to see if there's any thrust. Because if there's any thrust connected to it that is able to be scaled or adjusted due to input energy, now you can.
That's a big deal.
Yeah, so that's really the next thing, and I really welcome and others either taking this experiment, replicating it or extending it, or telling me, oh, you didn't think about this, or maybe try to do that, or providing some sort of materials or equipment or what have you. So I'm welcome and open to all of that.
Wonderful. Well, a big thank you to Dr. Chance Glen at Alabama A&M.
Yeah. And in Space City, Rocket City.
Rocket City, that's where to do it.
Yeah.